So I'm going to be recording this. Actually, I'm going to get rid of the webcam though. So we're not going to have the webcam there. All right. So the questions today, most people had trouble on 10 through 14. So I'm going to go over those first. So 10 through 14, I'm going to go over first. All right. Go over those ones first. And then after that, I'll go through one. And then after that, if you want to leave, if you got all the other ones, you're good to go. Feel free to leave and take off. But if you still want to stick around and go over those problems with me, stick around. Okay, and I'll mention that once we're done with 10 through 14. Okay. So before we even start, I just want to mention a few things here. All these problems you're going to be dealing with PV over T and PV over T. So the combined gas law. So like I said, I just memorized that one. I don't really think about the other ones, because then if temperature is constant, I can ignore temperature. If volume is constant, I can ignore volume and all that stuff. Then we also have the ideal gas law, PV equals nRT. Okay, and the caveat for that one is that pressure has to be in ATM, volume has to be in liters, N is always number of moles, R is a constant, and T has to be in Kelvin. Okay, the only caveat about PV over T and PV over T is that temperature has to be in Kelvin. Okay, temperature has to be in Kelvin. But pressure and volume can be in any units as long as you keep them consistent. Okay. All right. And then all the other things for like this one, the ATM, because it has to be an ATM. One ATM is 760 mmHg, or torr, same thing. 101.3 kPa. Those are really the only ones you need to know. You don't need to know PSI. I don't really do PSI too much. Okay. And then the other gas laws, you have Graham's law of diffusion, and then Dalton's law of partial pressures. I'm not going to write those down, but those are all the laws you need to know. Okay. So let's look at number 10. Let's start with number 10 here. So number 10. Let's zoom in on it a little bit here. A gas sample has a mass of 7.02 grams, occupies 31 milliliters at 64.3 degrees Celsius, and a pressure of 87 millimeters of mercury. Calculate the gas's density at STP. Okay, we want to calculate the gas's density at STP. I know I went over this one yesterday, I believe, for this class, but I'm just going to do it again. Can't hurt, right? So, where do we start here? Oh my goodness. Where do we start? Let's think here. Well, we know that there's 7.02 grams, but we want to know, we want to eventually calculate the volume. Like here we have if we want to find density, right? So density is mass over volume, right? We have mass. The mass is 7.02 grams. Okay, but we need to know volume. Okay, but we need to know volume at STP, 273 and 760 mmHg. Okay, we need to know volume at that temperature and pressure. Okay, now there's actually two ways to do this. So yesterday I taught you the PV equals nRT way. Okay, because we're looking for volume, right? So let me go over both ways how to do this. The first way is we can use these sets of volume and pressures, or pressure, volume, temperatures, and we can use P1 V1 over T1 equals P2 V2 over T2. I know I didn't do this way yesterday, right? So this is a different way to do it. Okay, I use P1 V1 over T1 equals P2 V2 over T2. So P1 was 87 mmHg. V1 was 31 milliliters. And T1 was 64.3 Celsius. But we have to convert that to Kelvin. So we have to add 273. So I'm going to do that. So 273 plus 64.3. So 337.3. Again, I just added 273 plus 273 here, and I got 337.3. And a lot of you are probably going like, oh my God, this is so much easier than the way we did it yesterday. And it kind of is. I just did it the other way. I don't know. I just felt like doing it the other way yesterday. But anyway, so we have P1V1 over T1 equals P2V2 over T2. So the second pressure is 760. The new volume, we don't know. That's what we're going to be looking for. And then the new temperature is 273. Okay. And then now we're going to solve for V2. There's two ways to solve for V2 here. Again, like there's many ways to do all these different ones. So we can do the cross multiplying method where we cross multiply and set them equal to each other. That works just fine. I prefer, well, I don't really have a preference, honestly. I'll do it one way one time and another way another time. Today I'm feeling a little bit different, so I'm going to do a little bit differently here. So we're going to get rid of this 273, so we put it up here because that divided by that is 1. And then we got to get rid of this 760, so I'm going to put 760 here. Okay. But if I do it to this side, I got to do it to this side. So 273 over 760. Okay. This will cancel with this. This will cancel with this. It's okay, Caleb. Okay. We're just going over number 10 on the work from yesterday. Okay. Now, so V2, so I'm just going to move V2 to the other side because I'm just going to make it V2 equals, bless me, 273 times 87 times 31 over 760 times 337.3. Thank you. Okay, so let's do the math here. So I'm doing 273 times 87 times 31. And then I'm doing divided by 760 and then divided by 337.3. And I get the volume to be equal to 2.87. Now, the volume is going to be in the same units that I used, and the units that I used was milliliters. So it's milliliters, 2.87 milliliters. Okay, so 2.87 milliliters is my volume. But that's not what they asked for. They asked for the density. So the mass was 7.02 grams. And then our volume is 2.87. Okay. And then we do that math right there. So 7.02 divided by 2.87. And we get 2.45 grams per milliliter. That is our density. So what do you guys think? Do you think that was easier than the method I showed you yesterday or about the same? Anyone? Does anyone remember? Yeah, I think that was easier too. Much easier. Much easier. The reason it was easier, we didn't have to convert any units, right? We didn't have to convert the pressure to ATM. We didn't have to convert the milliliters to liters. And then, yeah, I think it was easier. So, yeah, there you go. There's two different ways to do it. Okay, there's more than one way to do a lot of these problems. So you just got to kind of think it through and figure it out. Okay, all right. Let's look at number 11. So I'm going to erase all that. Again, I'm going to post this video, so I'm erasing it now, but the video will be up, and you can go back and look at it if you like. Okay, number 11. Okay. It says at 226K, a 1 gram gas sample in a 1.88 liter container exerts a pressure of 108 millimeters of mercury, what would the gas's sample density be in another container at a pressure of at 346 K and 68.3 mmHg? Okay, so here we have initial conditions: 226 K, 1.88 liters, 108.8 millimeters of mercury, and then we have some final conditions: 346 and 68.3, and we have the mass, right? The mass is 1 gram. So again, we can use either method. We could use the method I used yesterday. We can change the 1 gram to number of moles, solve for sorry, not change 1 gram to moles. Solve for number of moles using the initial conditions, and then solve for the volume in the second set of conditions. Or we can use P1V1 over T1 equals P2V2 over T2, which is the easier method. So let's do the easier method. Let's do it easier. So P1, so we're just going to use P1V1 over T1 equals P2V2 over T2. And we're going to solve for volume. We're going to solve for the second volume. And then we're going to take that 1 gram and put it over our new volume, and that will be our density. Okay. So we're going to have to solve for V2. Okay, so let's do it. And what's good about this is we don't have to convert any units because everything is in the appropriate units. So we're good to go here. Okay, so our original pressure is 108.8 and millimeters of mercury. The original volume is 1.88 liters. Don't forget that's liters, not milliliters now. And then our original temperature is 226. Okay. And our second pressure is 68.3 millimeters of mercury. So we already have the correct units. Our new volume, we don't know. Okay. And then our temperature is 346 K. Our new one is. Okay. Now, we got to solve for V2. So again, there's 2 ways we can do this. You could do cross multiplying and then solve it from there. Or you can just you have 68.3 on top and 346 on bottom. So I'm just going to do opposite. So I like it that way. I think it's faster and easier and more efficient. So 346 goes up here because we want to get rid of it. So we put it opposite of one another. And then 68.3 goes down here, and this actually works best when the variable is on top. If it's on bottom, it's easier to do cross multiplying. But anyway, so these 2 will cancel and these 2 will cancel. But we can't just do that. We have to do it. If we do it to one side, we got to do it to the other, just like your algebra teacher taught you, I hope. 346 up here and 68.3 down here. Okay, so our new volume is just equal to all this mess right here. So V2 equals, when I do the math here, I do, what are you doing, calculator? Okay, 346 times 108.8 times 1.88 divided by 68. I can't read my own handwriting here. 68.3 divided by 226. Anything on bottom, we just divide it by that, okay? Don't multiply. So the second volume is 4.58. Okay, now is it milliliters or liters? Well, in the problem we had liters, so that's liters. Okay, so then in order to figure out, okay, well, what is the density? It's 1 gram in 4.58 liters. So 1 divided by 4.58. And we get 0.22 or, yeah, 0.22 grams per liter. Okay. Now, technically, everything had at least 3 sig figs, so I should have it to 3 sig figs. So if you want to do it perfectly, it would be 0.218 grams per liter. But I'll take anything from 0.2 to 0.22, 0.218. You know, even if you got like 0.19 or something like that, I take it as long as it's close. Okay, but show your work, and you'll get credit. Okay, so that was number 11. So very similar to number 10. There was a reason I put those two together. You try number 10, you figure it out, then number 11 is easy. Okay. Next. If you guys have any questions, feel free to type them in the chat. Okay. Going to erase. But again, it'll be up on the video. Okay, next one. Ooh, we're getting it. This is going to be what we're kind of tackling next. Is this stoichiometry a little bit here? Okay. So this is a gas law stoichiometry problem, and that's actually the next thing we're going to tackle. But whatever, we got a little practice right now for it too. Okay, so number 12. Solid potassium chlorate, KClO3, decomposes to produce solid potassium chloride, an oxygen gas. What volume of oxygen gas measured at 40 degrees Celsius, 650 millimeters of mercury, will be produced when 13.5 grams of potassium chloride is decomposed? Okay. So first of all, we have to recognize this is not an STP. So we're going to have to... So this is not an STP, so we're actually going to have to figure out how many moles of oxygen we can make. And then we're going to take that number of moles and plug it into PV equals nRT. Oh, getting a little bit ahead of myself, yeah? So we want to know what volume of oxygen gas, right? But we're only given the grams of potassium chlorate. Okay, so this is actually, the first part of this is a stoichiometry problem. We start with 13.5 grams of potassium chloride, which is KClO3. And what we're going to do is we're going to figure out how many moles of O2 we can make. Okay, we want to know how many moles of O2 we can make. So what we're going to do is we're going to go from grams of KClO3 to moles of KClO3. Remember, it's pretty much always what we do in stoichiometry. If it's not already in moles, if it's already in moles, you don't have to convert it to moles. But here it isn't, so we have to convert it to moles. And then we're going to go from moles of KClO3 to moles of O2. Okay, so the molar mass of potassium chlorate, I'm going to add it up real quick here, is 122.55. So we have two conversions here. The arrows always indicate conversions, right? So first conversion is grams of KClO3 to moles of KClO3. So we use 1 mole of KClO3 over its molar mass, which is 122.55. And then we want to go to moles of O2. And this is the molar ratio. So molar ratio comes from the balanced chemical reaction. It's 3 O2 for every 2 KClO3. Okay, so we do 13.5 divided by 122.55 times 3 divided by 2. And we get 0.165. Okay, that's not the end, but we need that. Okay. Now we know how many moles of O2 we have. So we know how many moles of O2 we can make. Okay, but we don't want to know moles. We want to know how many liters, right? What volume of oxygen gas? Okay, now at STP, this would be easy because it's 22.4 liters per mole. But this is not an STP. So what we have to use is we have to use PV equals nRT. Okay, PV equals nRT. Okay. And our units have to be consistent here. We have to have, for pressure, we need ATM. So we're given 650 millimeters of mercury, and we have to convert that to ATM. So 1 ATM is 760 millimeters of mercury. Okay, so 650 divided by 760 is 0.86, 0.86 ATM. So that's our pressure. Our volume is given to us. We don't know volume. That's what we want to find. This is what we're trying to find. Okay. N is 0.165. And T was in Celsius. So T, we have to take 40 and add 273. So we get 313. Okay, a little sloppy here, but these are our numbers. Okay, so I converted everything. I suggest you actually write it all like more neatly than I just did it, but it's kind of hard to do it on this. As I go and talk and do all this, it's kind of hard to do it neatly. Okay, so let's plug in the numbers. So P is 0.86. V we don't know. Trying to find. N is 0.165. That's what we got from here. Okay. R is a constant. It's 0.0821. And T is 313. Okay. So we want to get volume by itself. So I'm going to divide by 0.86 to get rid of it. So volume will equal that. But if you do it to one side, you got to do it to the other. Okay. And when we do the work here, we do 0.165 times 0.0821 times 313 divided by 0.86, we get 4.93 liters. So our answer is 4.93 liters of O2. And I know I wrote 5, but close enough. The answer was 5 here, but. Okay, so again, we were given grams of KClO3. We figured out how many moles of O2 we can make using the balanced chemical reaction and stoichiometry. Then we took the number of moles and we plugged it into our ideal gas law equation, PV equals nRT, where N is the number of moles of O2. And we had to convert all of the units to the appropriate unit. So we had to convert millimeters of mercury to ATM, Celsius to Kelvin, and that was it. And then we plugged it all in and we got our liters of O2. Seems easy now, right? Maybe, maybe not, I don't know. Okay. Next problem. Okay, so I hope you noticed that there's a little bit of a pattern here for these ones, because number 13 is very much similar to the one we just did. It's pretty much the same thing. It's going to be the same method. Okay. Okay, so here we have solid iron chloride decomposed to produce iron and chlorine gas. What volume of chlorine gas measured at 71 degrees Celsius and 1.33 ATM will be produced when 98.4 grams of iron 2 chloride is decomposed? It's like the same problem, just different. A different form with a different reaction. Okay. So same thing here. So iron 2 chloride. Molar mass, I got to add that up real quick. Okay, so what we're going to do is we're going to take that delete. Okay, we're going to take that 90, we're going to take the grams of FeCl2. We're going to convert that to moles of FeCl2. Then we're going to convert that to moles of Cl2. Okay, so we have our 98.4 grams of FeCl2, and it's 1 mole over the molar mass of FeCl2, which I got to be 126.8. Let me make sure. Here. So where's my count? 70 plus. Yeah, that's pretty close. Okay. And then we have to use our molar ratio to figure out how much Cl2. So Cl2 and FeCl2. So molar ratio here. We get the molar ratio from the balanced chemical reaction. So it's 1 Cl. Oh, it's 1 to 1. Oh, super easy. 1 to 1. It's an equal number of moles. Okay, so let's do the math here. So 98.4 divided by 126.8, and we get 0.78. So 0.78 moles of Cl2. Okay, so that's our N value. All right, and we're going to use PV equals nRT. Okay, so another trick here, if you can solve, like, you want to solve for volume here. So even before you plug in numbers, you can solve for volume. So just divide by P. So V equals nRT over P. You could do that. Okay. N is 0.78. R is a constant, 0.0821. T was in Celsius, so we have to add 273. So add 273. So 71.7 plus 273, and we get 344.7. And then pressure, oh, it's already an ATM, thank goodness, 1.33. Make sure it's an ATM. Okay. Now we get the volume equals, and you just plug all that in. So 0.78 times 0.0821 times 344.7 divided by 1.33. And you get 16.6. Yeah, and my answer is 16.5. It's just rounding differences, not errors, differences. I use like the exact molar mass here. I probably rounded that one when I did the other answer. Okay. Beautiful, right? So easy now. Probably not, but it's okay. Okay. Next one. Number 14. Okay, number 14 says a 441 liter sample of nitrogen gas at a pressure of 68 millimeters of mercury is placed into a container of equal volume that already holds hydrogen gas at a pressure of 752.6 millimeters of mercury. What is the partial pressure of the nitrogen in the new container? What is the total pressure in the new container? Oh my goodness, this is a hard one. Okay. So let's think about this. So we have a 441 liter sample of nitrogen. That's what we start with at a pressure of this. And it's placed into a container of equal volume that already holds hydrogen gas at 725.6 millimeters of mercury. So basically you're taking one container, it's 441 liters, and has 688 millimeters of mercury of N2 gas. Okay, and then you have another one, same 441 liters, and it's 725.6 millimeters of mercury of H2 gas. Okay, and you're going to take this one and add it to this one. So this problem is actually super, super, super simple. All you're doing is you're taking the two pressures, so you're still going to have 725.6 millimeters of mercury worth of H2, and now you're going to have 688 millimeters of mercury of N2. So those pressures don't actually change. So that's the pressure of N2. This is the pressure of H2. Those pressures don't change. Okay. However, the total pressure in the container is going to change because now you add those two together. So you just add those two numbers together, and you get 1413.6 millimeters of mercury. I know, it seemed like a lot harder, right? Super easy though. Super, super easy. Okay. That was it. That's number 14. Pressure of N2 is the same as it started. Same thing with H2. And then the total pressure is just the two you add together. Super, super simple. Okay. Okay, I'm going to pause there for a second. See if you have any questions on 10 through 14. I can answer them.